Right, welcome everybody to the November meeting of the Mornington Peninsula Astronomical Society, and if you haven't QR coded yourself in yet, please do so, and also show your double VAT certificate to someone at the door as well if you haven't already done so. So we've got a few things have occurred in the last month or so of the Society. So showing that the top left there is a snap from Geoscience Australia showing details about the earthquake that occurred back on September the 22nd. And after the tea break, for those that wish to sit in on the video, I'll actually show the one that was released by the Geological Survey of Victoria, all about it, explaining about the earthquake, what actually caused it, and because it was actually the largest that's been recorded in Victoria. Next to it, we've had some solar activity for the month, and the first image to the right there is the view from the ISS with the aurora that occurred a couple of weeks ago. So that's a side-on view, so you can see some of the lights of the ground on the left-hand side, and the bluey green of the aurora as seen from the ISS. And to the right is actually, there we go, it should be flashing, is a view of the sun rotating. So in other words, you can see on that image there, and the screen I think is playing up a bit at the moment there. That's from NASA Goddard's Solar Dynamic Observatory, and what you're seeing there is every rotation is it varies between 24 and 30 days for the sun to revolve once about its axis, and it revolves faster at the equator than at the top, but as you see it's very, very active, and you can see that activity in certain wavelengths of light. And at the end of the meeting I'll actually show you a 5-year time lapse of the sun by that observatory, where they took one frame every 8 hours for 5 years, and very spectacular indeed. So, equipment's doing very strange things to me there. Here we go, back again.
It's a solar wind interference.
Clearly something going wrong there. Oh, lost it entirely. Now the other thing that happened last month, if you recall, was that William Shatner of Star Trek fame went up to the Kármán line, 100 kilometres above the Earth's surface, and you see Shatner down the bottom there, third from the left. Unfortunately, Glenn DeVries, who also went up with him, the one with the lightning bolt over his shoulder, he's now dead. He was killed in a Cessna plane crash just a couple of days ago. So just as well he went up and enjoyed the experience before then. It actually turns out that Shatner wasn't the first movie star approached. Tom Hanks was actually approached to go up and offered the seat for $28 million. But he sort of declined the kind offer of departing with that amount of money to actually go up. And down on the bottom right there is the very first movie that has been taken in space, a fiction type movie, has already had the raw footage taken up on the International Space Station, and shown there is the first actor slash actress, Yulia Peresild, a Russian mainstream actor, trained to be a cosmonaut, so she's officially has gone through the training, went up to the ISS on the 5th of October, launched from the Baikonur Cosmodrome in Kazakhstan, and came back on the 17th of October. And while she was up there, they started filming a full feature film, and it's going to be called The Challenge. And as I say, it's a fictional one about she plays a heart surgeon, goes up into space to save a cosmonaut. Now she was selected from 3,000 applicants for it, so she was very, very lucky indeed. Now apparently the ISS inside is a bit of a mess. It looks more like the inside of the Red Dwarf spacecraft, rather than like a Star Trek or a 2001 Space Odyssey that looks nice and clean and sparse. No, it's not like that at all. There's wires hanging everywhere like we have here, and bits and pieces hanging off everywhere, and so it'll be interesting to see what they got in the frame of the movie. Now apparently 40 minutes of the film will actually have been shot in space, so very first time this has ever been done. Now when she came back to Earth, they obviously had to carry her out the capsule, as they tend to do with cosmonauts who've been up there for several days at least. And she actually quoted that, she said, in zero gravity you feel like a feather, then everything is very heavy here. The head is very heavy, arms, legs, everything is spinning a little. And they showed a picture of her being carried out by two burly guys still strapped to a seat. Now, as I said, the sun has been very active, and this is the beginning of about 2 minutes of videotape that's being recorded by some of our members who are here tonight of the Aurora Australis that was visible on the peninsula on the 4th of November in the mid-evening, getting on for 9:30, 10 o'clock time. The one shown at the top there is Jamie, who's standing at the back of the room, and one lower left here is by Dave Rolfe, who's also standing at the back. Nerida's one captured on her smartphone is top right, and I'll press the play button in a moment. And Paul Alber's is just a still. Now these will be, they're not straight videos, they're a sequence of lots and lots of still images that have been stitched together to make a video. So they haven't used a video camera, they've used a regular type camera, but taken hundreds or thousands of shots and stitched them all together. Now what you'll hear in the background for the next 2 minutes while we go through the videos is what's known as Aurora Musicalis, and this was actually the sound of the aurora taken from Halley Base in Antarctica, which is the UK base from memory, down in Antarctica. And what you'll do is you'll hear hisses and pops and scratches, so it'll sound a bit like listening to a 1970s vinyl LP record that's a bit dusty, and as the needle goes over it you'll hear hisses and pops, and that is actually the sound of the aurora. So with that I'll press play and hopefully it plays. Right, so for tonight, welcome to anyone who's a new member of the Society. We might potentially have one or two here. Feel free to get up and leave at any time and go and have a cup of coffee at any time. We're not too formal. I'll go through quickly the events of the last month and what's coming up in the coming months before our next meeting. Then I'll throw over to Dr. Robert Colman from the Bureau of Meteorology, and he'll talk a little bit about climate change science. He's recently retired. We're very, very pleased to have him here. I think I first approached him back in 2019, and when he was still working for the Bureau of Meteorology, and then COVID came along, and then we were also had another lockdown after that, which meant that we had to wait even further. So this has been a long time in the coming, but we finally got there. Then after that talk, Mark will do Sky for the Month, and then I'll show the National Science Week meteorites competition winners that we had this year, and explain how we got those winners and what the correct answers were. Then after that we'll go into the video about the earthquake from the Geological Survey of Victoria, and then talk about the space environment of Earth, which is another one from the US, talking about the things that can go wrong with low Earth orbit satellites, including not only things like particles associated with the aurora when it comes down into the Earth's upper atmosphere, but also micrometeoroids, space junk. And in terms of space junk, you might have heard on the news about how the Russians just recently fired a missile up, an anti-satellite missile, blew up one of those and created a couple of thousand pieces extra of space junk up there. At the moment, I think the total count is about 1 million pieces up there, so they've added another couple of thousand onto all the junk that's up there. And that video actually explains that those pieces have about the momentum of like a 100-kilo steel safe flying at 100 kilometres an hour. So if they hit into something, they do an awful lot of damage, very, very small thing. And then at the end, we'll close there with as I say, this time-lapse from NASA Goddard's Orbiting Solar Observatory. So, recent events. Well, we just started opening up last month after we were allowed to come back together after this most recent outbreak. Had a couple of committee meetings to get it going, and also to look at coordinating the Brian Cox event, which several members took up to go up as a group for when he comes next year. We opened up on the 23rd of October on the Saturday, and members had a working bee and barbecue up here to try and get the place out of hibernation and functioning again. And we also finalised the calendar on the second one of those for sending out for 2022, which will come out in the next month or so. Now, we had a Scout Guides and Cup night due here on the 29th, but obviously that was cancelled due to COVID. And also because we've decided to focus on members for the rest of the year after opening rather than the public, so the public won't kick in until next year. Then on the 5th of November, one of our newest speakers, Manfred, who's not here tonight, gave a talk on small solar system bodies here instead of the public viewing night, so that was a members only one. So coming up soon, this Saturday, we've got the Telescope Learning Day here at the Briars, starting about 4 o'clock. There'll also be a barbecue as well, so if you wish to learn anything about telescopes and the basics of them, or ask any questions, or even bring your own along if you need some assistance with it, then feel free to come along. I don't think we have any booking for that. It's just a matter of turn up, and hopefully by November things will be eased a little bit more, but you never know. But that is usually mostly an outdoor event. Next committee meeting will be the Wednesday after. Then there'll be another one of the members viewing nights here at the Briars, with a talk given by Trevor. Unfortunately, Trevor was here, but then had to go because he left his phone at home, and hence his COVID certificate. So he had a nice journey down from Bentley for no reason, unfortunately. But he'll be here on the 3rd of December for that members viewing night. Christmas dinner is on Saturday the 11th of December. Booking is absolutely essential online for that, so that we can organise the catering, and all members of the society are welcome to come along to that. There's no meeting in December for the Society, so this is the final one of these third Wednesday of the month meeting for the year. The next one will be in January, on the 19th of January. Public stargazing nights start on first Friday of January, which is 7th of January, and then this year will be every Friday in January as well, as we try to catch up, because there's quite a backlog of people that we unfortunately had to cancel their visit to the previous public stargazing nights because of COVID. We then move on to our talk by Dr. Robert Colman, Rob was retired head of climate change at the Bureau of Meteorology, so only fairly recently retired, and he'd been there for over 30 years, so he's made definitely a career in climate change. He did his PhD in physics at the University of Melbourne before deciding to see the light and change completely field to climate and the weather, which of course really is physics in disguise. So not too different there. He's also a past lead author of the 4th Intergovernment Assessment Report on Climate Change, which was a co-winner of the 2007 Nobel Peace Prize. And he's also a review editor of the current 6th Assessment Report as well. So very well respected internationally. He's also said that if you have any questions as we're going along, please ask them. You might want to put your hand up. Bear in mind that where you're wearing face masks, it can be very difficult to hear you, so please speak up as loudly as you can if you have a question. And if you have a question, ask it there and then, don't save it until the end, because if you're asking a question, the chances are several other people have exactly the same thing. Well, with that, can I ask you to give a round of applause to Colman?
Okay, so thanks for the introduction, Peter, and look, thanks for the opportunity to speak at this illustrious organisation. I was really looking forward to coming down here for the last 2 years. In fact, I've been looking forward to coming down here. So, look, thanks for persisting. So actually, the 2-year delay has been advantageous because a couple of very interesting things have happened. Since in fact 3 interesting things have happened in the last a couple of years that are very relevant to climate. Of course, one is COVID, and we'll see in this talk, hopefully, how COVID has affected climate. The second one is IPCC, which I'll just talk a little bit more about further in the talk, released the 6th Assessment Report. And the third, of course, we had COP26 at Glasgow. I see some people shaking their heads already. But so I'll talk about COP26, but I won't talk about it like giving the Australian government a report card or something. But I'll ask the question: has that actually been a step forward? Has COP26 for climate, has it actually made a difference? Yeah. And you said no. Well, we'll see. But so, as Peter said, look, please ask any questions. It's often hard to know sort of how to pitch a talk like this. Some people, I'm sure, know a lot about climate change, and other people may know significantly less. But I wear hearing aids, so if you have a question, you've really got to probably shout it at me, otherwise I won't answer that question. So the outline of the talk, what I'll talk about, I thought an astronomical society, right? So I'll talk about the greenhouse effect. So climate of planet Earth and why it is what it is, the natural greenhouse effect. Then have a look at what climate changes we've seen to date in the record. Briefly, what's caused them and how we're so certain that it's humans that have caused these changes. Then a look into the future, what might happen down the track. And then I've got this 2021, where are we tracking on emissions and what's the outlook for stabilising the climate. So I'll start with the greenhouse effect, and as I said, some people I know will know a lot about this. Of course, we have the sun beating down on the Earth, and it's over 1,000 watts every square metre. It hits the top of the atmosphere. But if you average over the whole planet, it's about 240 watts for every square metre, like a couple of light globes per square metre, relentlessly, day and night, summer and winter. Now, of course, the Earth, to stay in equilibrium, to stay at a stable climate, has to get rid of that heat. And so, I think people will be aware that all bodies in the universe actually radiate heat out from them. And it's a sensitive function of temperature how much they radiate out. So the Earth radiates out not in visible light, but in infrared light. So we can't see it, but it's radiating all the time all around us. Okay? So the Earth must re-radiate that 240 watts to stay in balance. So what's the natural greenhouse effect? So the natural greenhouse effects, we say the solar radiation comes in, bounces off clouds and reflects off snow and ice and this kind of thing. That 240 watts gets to the surface, and what happens is the surface tries to radiate that to space. Okay, but you'll see this this sort of thick orange line that then comes back. It doesn't get that far, and that's because some of that infrared radiation is absorbed by molecules in the atmosphere, right? And we'll come back to what are the most important. And once it's absorbed up there, say a kilometre up, it then re-radiates in all directions. So some of it will radiate out to space, fine, we'll find out to space. But some of it will radiate back downwards. So you see this radiation sort of bouncing all around in the atmosphere, and it's sort of hard for it to get out because of this absorption and re-radiation. So that's the normal greenhouse effect. And if we didn't have that atmosphere there, if we didn't have that natural greenhouse effect, the global temperature would be around minus 20 degrees or so. And in fact, it's a balmy 15 degrees. So the atmosphere and the natural greenhouse effect keeps the planet more than 30 degrees warmer than it would otherwise be. So that's in fact, so when we talk about the greenhouse effect from human emissions, it's really the enhanced greenhouse effect. We add to that, and it causes even more trapping. Okay. So what gases are responsible for the natural greenhouse effect? And so we've got here the breakdown of the, so nitrogen 78%, oxygen's, I said 78%, that's right, sorry, what that should be, but 78 minus like 28%, and nearly up to 100%, sorry, that's a typo. And carbon dioxide down here is at 0.4%, water vapour is about 2 to 3%, and methane, which is also an important gas, is really down at this really trace level. So a major step forward in climate science took place in the late 19th century. This guy here, Spencer Ramus, by measuring things in the laboratory, he concluded in this quaint, lovely language that selective absorption of the atmosphere is not exerted by the chief mass of air, but in high degree by aqueous water vapour and carbonic acid. So we knew then that the key constituents of the atmosphere for the greenhouse effect, water vapour, carbon dioxide, and there are others as well. Now, that's quite low, right? 0.04%. And I've seen, perhaps from the sceptical side of things more than elsewhere, perhaps the argument of incredulity. How can 0.04% changes to such a small quantity really make a difference? Like, it's like, how can 0.04% make any difference? And the answer is because, I'll show you in a minute, it's actually a very, very strong emitter. Then we know that small amounts of things can make a big difference, like a COVID virus, a very small thing, right? It makes a big difference. But I think the best argument is this argument, whereby 0.05 really can make a big difference, right? So if you don't believe that 0.04 makes a difference, then I suggest the next time that this gentleman approaches you, you just say, look, 0.05, it's a tiny amount, it can't make any difference.
Doesn't cut any ice.
So, look, it's an astronomical society, so I've added this slide, and I don't know anything other about other planet atmospheres. So I'm hoping someone will be able to give me some information about this. But just interesting to compare that Earth has a very, very small amount of carbon dioxide, where the atmospheres of Venus and Mars are both extremely dominated by carbon dioxide. So, of course, Venus is in a runaway greenhouse effect, and Mars is very cold with a very thin atmosphere. So I'm not going to talk any more about those planets, but if someone can answer to me I would love to know why carbon dioxide is so predominant in the atmosphere of other planets. So why is CO2 such a critical greenhouse gas? And the answer is there are three reasons carbon dioxide is so important and so important for causing enhanced greenhouse effect. For a start, it has a huge appetite for that outgoing radiation called terrestrial radiation. Right? So it's this very strong absorber of that radiation. There are other stronger absorbers though. Things like CFCs, even methane, molecule for molecule, is a stronger absorber. So it's not just because it's strong, it's also we're emitting colossal amounts of it. So we're emitting much more of that than we are of CFCs, much more of that than we are of methane. So I've got a plot here that shows from the 1960s onwards the global CO2 emissions from the burning from burning fossil fuels. And you'll see bumps and wiggles and things, and you see that, there have been, sometimes when we get a downturn, it does cause, like the GFC causes a little thing, but there are blips on this relentless increase in carbon emissions that we've had. And I've stopped it in 2019, and I'll show you what 2020 and 2021 look like at the end of the talk, once you've got to stay awake long enough to see what COVID does and whether that solved our problems for us. So we're emitting a lot of it. And the third very important reason why carbon dioxide is such an important gas is because it has a very long lifetime in the atmosphere. And what I mean by that is you drive your car down the freeway and you emit a kilo of carbon dioxide. 50% of that stays in the atmosphere for a very long time. And what I mean by a very long time is hundreds or thousands of years. Okay. So the processes that remove carbon dioxide are sort of on geological timescales. So in other words, what we emit accumulates in the atmosphere. In fact, we know very well where the carbon dioxide goes, and so you'll see that actually it doesn't all go into the atmosphere. So here are our carbon dioxide sources. Remember, we had about 40 gigatons. A gigaton is a billion tons, right? 1,000 billion tons. So we emit about 40 gigatons per year. So most of it, 90% of it comes from burning, and then there's deforestation also occurring. So where does it go? About a quarter of it, that's 10 gigatons per year, is taken up by the ocean. So carbon dioxide dissolves in water to an extent, and so the extra carbon dioxide you inject into the atmosphere, some of it actually goes into the ocean. So the ocean's providing us a service here, really. So it's taking up a quarter of what we emit. I won't talk about it, but there's a nasty little kicker to it. As it gets absorbed in the ocean, it actually increases the acidity of the ocean, so it reduces the pH level of the ocean, which can have profound effects on sea life, on the formation of shells and so forth. Another roughly quarter of it goes into the terrestrial biosphere, so into planets. And this is like a CO2 fertilization thing. So when plants like CO2, right? So when there's more CO2 there, they grow thicker, and particular areas of Australia where they're in the savannas, in the tropical savannas, there's been a noticeable thickening of the growth that's there, sort of more dense vegetation that's there. So a quarter of it's going into vegetation, 30%, and roughly half of it goes into the atmosphere and stays there for long periods of time. Okay, so that's the kind of breakdown of what we call the carbon budget. Now remember, Svante Arrhenius said, okay, water vapour is actually the other one that's really important. So people sometimes say, well, what about water vapour? Isn't water vapour so important that we can really forget about CO2? And the answer is no. They're very closely linked together. We don't affect water vapour directly, right? So it's not like CO2. You don't put water vapour, from your sprinkler doesn't like just head up, you water your garden, doesn't just like accumulate in the atmosphere, right? It rains out very quickly. But what happens with water vapour is once CO2 or methane or whatever starts a temperature increase, then that produces that warmer atmosphere, holds more water vapour, like you get off the plane in Cairns or whatever, you feel the heat, feel the humidity. And then that traps more of this out, this terrestrial radiation, and that in turn warms the planet, which increases the amount of water vapour and so forth. So this is like a positive feedback. It's a positive feedback in the system. And water vapour is the most important one. So that's how we affect water vapour, but only indirectly through carbon dioxide and so forth. So it's a positive feedback, but it's not a runaway feedback, right? So it's not like the microphone where there's the whistling in it that's a runaway feedback. But what it does is it amplifies it a bit. So water vapour roughly doubles the amount of warming that we would get from carbon dioxide. Right? So we'll see in a minute that we've warmed by about 1 degree. If it wasn't for the carbon dioxide response, we would have warmed by about 0.5 degree. Okay, so that's the constituents of the atmosphere and what's important. So how have they changed? Again, people will have seen this plot, I'm sure. So in the 50s, they started monitoring atmospheric CO2 in Hawaii. And there was a bit of scepticism actually as to why you would bother doing that, but it meant we've got this incredible record. And what you see is from about, this is 0.03, so I now express this in parts per million. Okay. So we had about 315 parts per million, and it's gone now to over 410 parts per million over that period. And it's a nice, it's a scary plot, but it's a nice plot too. You also see the sort of wiggles on the thing. And wiggles, of course, are the breathing of the biosphere. So in northern forests, when in spring, there's growth of leaves and it sucks CO2 out of the atmosphere, and then in the fall, it's released. So you see this natural cycle, and then there's this. And I can't go away from here without a plug for our own Cape Rim, which is actually this beautiful part of Tasmania, where CSIRO and the Bureau have been taking measurements since the 70s, and they show the same thing. Okay. Yes?
What's the natural concentration before humans started to, of CO2? What's the...
That's a perfect question. It's the next slide. Right, so in fact, the answer is, so here's the paleo perspective, and actually people have seen Al Gore's film, Inconvenient Truth. They'll be very familiar with this plot. And he's on this sort of raising platform when he shows this. Does this really well, so I can't do that really well. But of course, we look, we can go back past 1950 by looking at bubbles in sea ice. This is already in ice. And so before you calculate or extract an ice core, say from Antarctica, this is Antarctic. War Dome is an Australian, where an Australian base down there. And this shows carbon dioxide concentration and thousands of years before present, so this goes back 800,000 years. And you see the little bubbles in here, you can extract them. And you see before now, we had this, it was ricocheting around between about 200 and perhaps the maximum 300, you see here. Of course, these fluctuations on this long time, so this is ice ages, this is past ice ages. So when it's cold, CO2 levels are low in the atmosphere. And when it's high, we're in interglacial, and of course we're in interglacial now before it kicked off. So the answer to your question is about 270 parts per million, it's now 410. But CO2 plays an important role in this. It doesn't kick off the ice age, but CO2 levels help amplify. I really haven't got time to talk much about that. Two key takeaways from this is CO2 levels are higher than they've been for 2 million years. And at least 2 million years, we can't, And the rate of CO2 increase, even in these really rapid warming, were less than a tenth what they have been in the last century. And methane levels are around 250% of what they were pre-industrial. Nitrous oxide, which is another important greenhouse gas, is about 40% higher. So the temperature changes, again, people have seen this. This was up to 2020. This is global temperature, land and ocean. And so we can get reasonably reliable records back to the late 19th century. And we see this sort of rapid warming that's occurred really since the 70s. So this is, there's a lot of fluctuation here, of course, and this is natural variability and also volcanoes, some of it's volcanoes. So I should have marked Venezuela on here, which I think was 1991. 1991. So 1991, that's maybe it's here I'm making. But anyway, they have an effect, maybe half a degree, a big explosive volcano like that. And this is El Nino and La Nina. So during an El Nino year, the planet's warmer, La Nina it's cooler, and so forth. An important thing to take back from this, though, is so we warm 1.1 degrees. But in fact, that hides something that people don't often really talk about. The land is actually warmed by 1.6 degrees, and the ocean, which heats slower than land, partly because of that thermal inertia of the ocean, only warmed 0.9 degrees. So land is warm, is increasing at sort of like, another 30% on top of it. So of course, just thinking when we look to the future and talk about restraining climate change to 2 degrees, for land that means 3 degrees. Okay, so we always must. It's often we really should talk about. Yep.
When you say land, you mean air.
I mean land. I mean land surface. Yeah. So these measurements, they're either sea surface temperature, right? So right on the surface of the ocean, or else they're sort of Stevenson screen type 1.5 metre surface air temperature. But the difference between the skin of the Earth and that is not very different. Yeah.
Well, I told you earlier on before you started, I went to the North Pole in 2015, but 3 years ago, my partner and I, we went to see the daughter in Ingham, which is 100 kilometres from Townsville. And there was smoke billowing out of this sugar refinery like there was no tomorrow. And I come back here and the same thing happens over at S.O. Billiton. And when I wrote to both the parties why they wasn't doing anything about it, the box seemed to be going round and round in circles and nobody was doing anything about it, like as far as I'm concerned, we're doing nothing about it today. So I ask you the question, what is the real problem? We're faced with a crisis, and David Attenborough had been saying it for 50 years, the Beatles said it 60 years before that, and we're still no better off for what it is,
I've got 2 slides that we've seen.
Sorry?
I've got 2 slides coming up that hopefully will address some of that and also maybe share your frustration as well. Australian temperatures reliable maybe from 1910 and as consistent with the record I showed before. So Australia is warmed by about 1.4 degrees. Just keep it on time here so don't separate on too much. So that's it. Now, an important thing is we don't feel the average temperature, right? You don't go out and feel it's not 15 degrees every day, even though that's the average global temperature, obviously. So we get this warming, but we often feel the effect of extremes, okay, as does the ecosystem. And so along with that change in the average, we've seen a disproportionate increase in extremes. So why do we see a disproportionate increase? You can imagine the temperature sitting on this bell curve. Sometimes it's really hot, sometimes it's really cold. These really hot extremes, like 45 degrees in Melbourne, right down to the tail of this distribution. if you move that whole distribution across, suddenly that 45 degrees is getting into the major part of the distribution itself. So you get extremes far more frequently. It also, the other thing that the warming does is that it pumps up the hydrological cycle. Okay, so the air holds more water. When it rains more heavily. When you have a drought, the drought is more severe because evaporation is stronger. And so it can be associated with, fire weather, which is associated with drought, and high temperatures becomes more severe. So we experience a lot of the change through extremes, but I won't talk more about that, but climate change has a profound effect on extremes, and that's where a lot of the impact comes from. I'll talk now about just rainfall patterns, and just very quickly, I'll put just one slide on this. So temperature is one thing, but it also, as the globe warms, it also affects the patterns of temperature, of rainfall. And specifically what it tends to do in the Australian region is during winter, low pressure systems that hit Melbourne, and it's cold and it rains a lot, they tend to get pushed a little bit further to the south. And so as the temperature warms, they just relentlessly sort of get pushed. So some of those low pressure systems start to miss the country altogether, and it rains over the southern ocean, over the ocean only. So the effect of this is the last 20 years of the record compared to the full record. And you can see that in the cool season, there's been this really marked drying right across the southern half of the continent. Now it's hard to argue, I mean, it's rained a lot lately, of course, but that's weather. This is, on long time scales, there's a significant drying going on.
Is that consistent with the model forecasts?
What's that?
Is it consistent with what the models are forecasting?
For the next 3 months, or for
Well, no, for the long term. Is it going to get drier in Victoria?
Yes. Yeah. So the forecast is for the projection. We call it a projection because it depends on the emissions, right? But the projection is for this to continue. Yeah. Because that process is sort of well understood. Yep.
That climatic phenomenon that is called El Nino, how much effect has that had on climate change over the years? They call it, the Spanish call it the child in Chile.
Yeah.
Drought on one side, floods on the other, and it seems to have tied in with climate change. How much effect would it have had?
Okay, so El Nino causes those blips and jumps, and you saw particularly in the Australian record, there was a lot of variability year to year. Right? So El Nino will continue to operate, and so El Ninos and La Ninas will continue to operate in the warmer climate. Right? So we're confident they will continue. How they affect the country, though, will probably be changed, because, as I said, the hydrological cycle is a bit pumped up. Right, so when we're dry from an El Nino, we might expect it to be a bit drier than it was before, previously, without climate change. And when it's wet during La Nina, we might expect also more intense rainfall and so forth. So I'll keep on moving. So sea ice and snow loss that I won't talk about, but it's very well documented. Melting in Greenland and some ice shelf instability, and of course loss of Arctic sea ice. Here's perhaps a somewhat more technical plot, though, that is actually carries an important point. This is actually ocean heat content. So ocean heat content is a measure of the total heat that's stored in the ocean, right? And sort of averaging the heat over the full depth of the ocean. And if you look at that, that has been relentlessly going up. And you can measure that from, like drifting buoys and, the things you throw off ships and this sort of stuff. And the key point is that extra heat that's being trapped, most of it is going into the ocean. And again, the ocean is doing us a favour here, right? So the land surface is warming up, but the ocean is also warming up and takes 90% of that extra energy is going to the ocean. If it wasn't for the oceans, that we would be experiencing much more rapid climate change. So the oceans are doing us a favour. The downside of it is that that as the oceans store that enormous amount of heat, if we then reduce the burden of greenhouse gases and want to bring temperatures back down, there's enormous thermal inertia in the ocean. It will take decades or centuries for the oceans to cool down. So that's what makes that, and the infinite lifetime of CO2 in the atmosphere is what makes it so committing, such a committing thing. That it's almost irreversible. I wasn't sure where to put this in, but I want to mention IPCC here. Actually, let's get a show of hands. Who's heard of IPCC? Who knows of the International Panel on Climate Change? Yeah, so they a bit more. So I mention this because they just released the 6th assessment report, and IPCC is like the gold standard of climate change understanding of science, and I'm going to show quite a few figures from IPCC just coming up next. So IPCC is an intergovernmental UN-based program. So it's agreement between governments, but it's written by scientists. And since 1990 to 2021, we've had IPCC reports, and each one sort of sums up the state of the science on climate change. IPCC reports policy relevant, not policy prescriptive. And in answer to the question you had, of like frustration, there is a certain amount of frustration, of course, from scientists that worked in the area since 1990 of
the impression.
You know what they did. So I put this up. So just of you know, you can read for yourself. 2009 is this thing on. It's perhaps the message has gotten through. You know, perhaps it now has. But it's been a long time coming, right? So back in 1990, we were very confident of climate change, and we're now all too confident of climate change. How are we going for time? I don't want to just sort of grab it on.
Yep.
So
there's a clock on the back wall there. Can you see?
Oh yeah, okay. So how are we so sure that humans have caused the warming? Actually, I don't think I'll talk much about that. But IPCC has come out and said, so the last assessment report said it's unequivocal that human influence has warmed the sea. Now it's interesting and unusual word to use unequivocal is because scientists don't like to use the word certain. Certain, nothing's ever certain, but unequivocal means certain, and so it's certain as we can be that human influence has caused this, and moreover, we're very confident that it's caused almost all of the warming that's been seen. I'll show this plot. It's just one of the lines of evidence of why we're so confident that it's been caused by humans. I haven't talked about climate models, and I won't really talk about climate models, but climate models are our sort of representation, mathematical representation of the laws of physics and so forth that we run on supercomputers. Like weather forecasting models that we run for centuries instead of just for the next week. Okay. And you can get these models, and the good thing about them is you can say, put into this atmosphere of your model whatever gases you want to do. So you can run these models in many ways. And this shows models run in two separate ways. For starts, here the black line is what's been observed in the warming over the last century and a bit. The blue line and this cloud around it just means we've run 40 different climate models with different assumptions. Show what happens if we just give those, say CO2 didn't increase, methane doesn't increase, we just allow for solar changes, like changes in the solar cycle, volcanoes, natural gas. And this is what they say happens. If you put in our best estimates of what these greenhouse gas changes and so forth, then you get this, which is really quite a nice match of what's happening. So what it says is we can't explain it says two things. We can't explain the warming without the emissions that we've seen. And secondly, the emissions we've seen are about the right size to explain the warming we've seen. So it's not just that we cause warming, but we cause warming of about the amount that we've seen. Okay. So let me tell you about one other thing for completeness. Okay. And it's not about greenhouse gas, it's about other human effect on the atmosphere. Here's the observed warming that we've had, 1.1 degrees. Okay. Now what you can do using climate models and other information is you can break that down into what contributes to it. So internal variability, almost nothing. Solar and volcanic, almost nothing. Greenhouse gases, the jargon is well mixed greenhouse gases. That's carbon dioxide, methane, nitrous oxide, CFCs and so forth. Have caused about 1.5 degrees of warming. Hold on, we've caused 1.5 degrees of warming. Other human drivers have actually cooled the climate. And so some of our emissions have actually had the opposite effect. They've caused offsetting cooling. And it's important that we understand these, and they're called aerosols. So the jargon is aerosols. An aerosol is not a spray can aerosol, right? It's an aerosol is a tiny particle like of dust or soot, you know, like a very, very small particle suspended in the atmosphere, like this from a smoke plume. And we produce a lot of them. And it's called pollution, right? So, you know, it's living hazes and so forth. And so what you find is, even though soot and dust, it looks dark, right? You know, you think, oh, you know, that's going to absorb, you know, sunlight or whatever. In fact, it reflects it. Some is absorbed, but a lot's reflected. And so what these aerosols do, what this pollution does, is it reflects away some of that solar energy, and it also affects clouds, because cloud droplets form on these nuclei. And of course, it's in very specific parts of the world, there's a lot of industrialisation. But this is a very important thing, okay, because these aerosols are offsetting. They're doing us a service. This pollution is doing us a service, climate-wise. Right? It's bad for your lungs, it's killing people, it's a horrific problem. But for the climate, it's offset the warming by nearly half a degree. So that's what's happening with them. A key thing, though, is we need to get rid of this, right? Because it's a health hazard, and the world is getting that, and so that offsetting that will occur will sort of ramp down as we get pollution more under control.
So I've got a question about that. So,
yeah.
So if we stop emitting greenhouse gases and so
Yeah.
on, presumably we're also going to lower the amount of aerosols in the atmosphere.
Yeah.
So we're going to reduce that negative impact. So might we start, first of all, to see it warm more?
Yeah. Yeah.
And
So
will that be an issue for convincing the silly politicians? Or?
Well, yeah, I don't know. I mean, you want to get rid of this stuff. Right?
Yeah, obviously.
It's bad. So it's just an unfortunate side effect of it that it will also exacerbate.
But
so there's hidden warming that we haven't been exposed to yet, like another 0.4 of a degree.
And so governments understand that we might see warming increase as we decrease our emissions.
Well-informed governments would understand.
No ours.
Another critical difference with doing aerosols, of course, is they rain out quickly. So you see the average particle up there only lasts a couple of weeks before it's rained out, unless it's injected into the stratosphere. So that's why Pinatubo called the planet, because it injected aerosols above the weather, and there it can last for months or years. But when it's below, when it's in the lower parts of the atmosphere, it rains out pretty quickly. Actually, interestingly, this reflecting thing, it played out during the bushfires in 2019. So when the Bureau was doing forecasts remember there were huge smoke plumes over the East Coast, and the Bureau would take the weather forecasts for particular towns that had a lot of smoke over them and reduce the temperature forecast for the day by a couple of degrees. So actually having a big smoke deck over you actually cooled some of those towns below what they would have been. You sort of don't think of it, but that's what it does. So anyway, that's aerosols. So let's look at the future. And there's a bit of crystal ball gazing. So what the climate science community has done about trying to predict the future on decades ahead is it went to the, we don't know what's going to happen with the emissions. So the scientific community went to the socio-economic community, to other communities, and said, come up with some different future pathways of what emissions might look like. And they're called socio-economic pathways, SSPs is the jargon. Don't worry about the number here, that doesn't mean temperature or anything, it's just it's a label with an obscure meaning. But here we are, 40 gigatons of carbon dioxide per year, and you can have all sorts of assumptions. This sort of business as usual, just plow on and just keep going up. We're already going up, keep on going up, through to a little bit of mitigation, through to flatten it, and through to these very strong mitigation scenarios. Okay. So what we do, and in fact, you see some of these go negative, and I'll come back to what going negative means. And so what the climate community does, the CC does this, is to get your climate model and you run it, you force it with these future scenarios, and then you see what warming you get. So here it is from the 6th assessment report. This is the warming we've had of about 1 degree. And then from here on, we choose one of these pathways, either sort of business as usual or strong mitigation. And you'll see business as usual, you're getting up nearly 5 degrees. And with this sort of very strong mitigation, you're levelling out at about 2 degrees or so. And two important things I'd like to just draw your attention to. Over the next decade or so, no matter what pathway we go down, it's not going to be dramatically different. There's a lot of committed warming already in the system. We're still really catching up with that. The ocean's still catching up. But by the time we get to the last couple of decades of this century, it's all the difference in the world. Right? And so, kids and grandkids, the world that they inherit will be very, very different depending on what pathway we choose to go down. So, of course, I'll now talk about Paris and then talk about Glasgow, and then I think that's it. So the Paris Agreement, everyone knows this, global goal to hold average temperature increase to well below 2 degrees, that's from pre-industrial, we're at 1.1, and pursue efforts to keep warming below 1.5. And we already might be a bit sceptical here, right? If we get rid of aerosols, we're already bang, we're at 1.5. But let's just put that aside for a moment. And this kind of technical looking plot, perhaps, there's a lot of information here. But I'll distill it. It says the climate's complicated and all these feedbacks and processes or whatever. But when it boils down to it, there's actually a very simple linear relationship between the total amount of carbon dioxide and other greenhouse gases that we've emitted since pre-industrial times and the final temperature you arrive at. So the more you emit, the higher the temperature goes. So here we are in 2021. This axis is thousands of gigatons, so like these teratons or something. We emitted about 2.4 gigatons of carbon. And here's the final warming you might expect. So if we want to end up at 1.5 degrees, we've got to follow really one of these very, very strongly mitigating pathways. If we keep going, then we'll just get warmer and warmer. Okay? So if we want to stop, say at 1.5, then this immediately tells us what our final budget is. So the final budget is just over 3,000 gigatons, and it's kind of like your home budget or whatever. You blow that, you've gone past it, you go to a higher temperature. So this idea of a final budget is, I think, a very powerful one, and that really tells us what we need to do. So how much budget have we got left for these? So here's what we've emitted: 2,500 gigatons of carbon since the start of the Industrial Revolution. And if we want to stay at 1.5, we've got about 420 left. Now we're burning it at about 40 gigatons per year, so in 10 or 11 years it's gone, right? So at the current rates we are, that's never again obtainable if we have to drop to zero instantly from there. And you see if we want to stabilise at 1.7 or 2, we have a bigger budget and we have more years left, right, to get to 1 or 2. Sorry, to 1.7 or 2. So that's the sort of a budget concept of this. How do we get there? Like, what pathway would give us that budget? Right? And so this is where these numbers of cuts by 2050 and 2030 come from. So let me show you this, and it takes a bit of explaining, but it's an important figure. So this came from an IPCC report in 2019, and it asked, what do we need to do to stop at 1.5? What do we need to do to stop at 2? So here's the year. We're about here. In fact, we're here. And here's the emissions that we have, about 40 gigatons of carbon per year. And these pathways, there are many ways to stabilise, because there's not just a single way to do it. The green ones here end up at 1.5 degrees of warming, and the grey ones also end up at 1.5 degrees of warming, but they overshoot in the meantime. So they might go to 2 degrees of warming and then you pull it back to 1.5, right? So it's got overshoot. So let's just look at the green lines for a moment. And it doesn't matter which of these you look at, this one will do. And we see by 2030, to be on this pathway, we've got to be around 20 gigatons. Okay. So that's where the 50% cut by 2030 comes from, to try to make this. Okay. And what happens later? So you push it out to 2050, and you see they start to cross this axis here. So that's saying you're very close to 2050, depending on the exact pathway, you've got to be close to zero. So it's zero globally, no emissions, right? Or net zero emissions. And in fact, there's a little bit of overshoot. So to actually stay at 1.5, you've got to go negative. Okay. So below the line. And so negative means, of course, you not only have zero net emissions, but you're actually physically pulling CO2 out of the atmosphere. So, like whatever, we can talk further about how that could possibly be done on the next one. Right, and so by the time you get at 27, you're having to pull out to 5 gigatons. If we follow the grey path and don't cut very rapidly, so we just cut a little bit by 2030, then we can still end up at 1.5, but you see between 2030 and 2050, this is much steeper than this one, right? So really got to between 2030 and 2050, you have to really put the, get going. And also it has much more overshoot. So in other words, by emitting this extra here, we would commit ourselves, if we really wanted to get to 1.5, then we'd have to be pulling, say, 10 to 20 gigatons per year of carbon out of the atmosphere. That's a lot. So anyway, that sort of sums it up of where we are. So that's to stabilise at 1.5. 2, it pushes out a little bit more. And so you've got a little bit more time, but you've still got to cross this line. But it's about 2070 or something. You've still got to get to net zero. So how are we tracking? Okay, so this is now the last few slides really, but just sort of where are we tracking and what's Glasgow saying? So here are global fossil CO2 emissions, and I've now included 2020 where we dropped, and 2021 it's not yet over, but that's projected on what we've emitted so far, and we're already in November, right? So we're bouncing back up. And I'll zoom in on that bit there. Oh, sorry, here's what Australia's done too. Australia. So Australia increased and then has been flat and then dropped in 2020. And I haven't got figures, so I haven't got 2021 data for Australia, no doubt jumped back up. So we'll probably just remain flat. So what happened in COVID? So here's the emissions now. We're 37 gigatons down to 34 and a bit gigatons. And so what happened when COVID came in is we dropped, and that drop was made up by this drop in coal, 0.6 gigatons of coal, significant drop in oil usage, gas usage also dropped. And then when we went up to 2021, coal jumped back up, in fact more than it had dropped, so it actually net increased. Gas also jumped up more than it had decreased. Only oil was less, I won't talk about cement, but only oil was less, and of course oil's use is still suppressed by travel and transportation and so forth. So we have dropped very slightly overall, but you can see the sort of bouncing up and down. Australia, where we sit in Australia, so this is just to show energy consumption in Australia, where we are. So I found this an interesting plot. Here's the total energy use in Australia. Coal, which actually peaked in around 2009 or something, and has been dropping ever since. But that's been made up for by oil increased usage. Let's ignore 2020 here for a moment with that drop. And gas increase has made up for the drop in coal. And we see increases in solar and wind and other things, but solar, and there are a lot of solar on rooftops, right? But it's still a very, very small player in Australia, unfortunately. Okay, and the last couple of slides I'll talk about Glasgow, and so what happened in Glasgow. Australia got an F minus.
Yeah, well, I was all ready to go. I was all ready to go. I was going. I should have been there.
Well, you should have gone. You might have made the difference. Right? But it's but you were stuck at the North Pole. You were stuck at the North Pole. I think it was.
No, Mum told me to stop there when I come back.
But okay, so Australia. I won't talk about Australia. We've got an F minus where the fossil dinosaurs. No doubt about that. But lots of other countries made commitments, right? So even we made a 2050 commitment for what it's worth, and lots of countries made 2030 commitments. So has that made a difference? That's the question. So here are those IPCC scenarios. Remember the SSPs, and so if we were to follow these very high ones, we'd end up at say 4 degrees of warming. 4 degrees of warming would be horrific. That's 4 degrees of global warming. That's like 5 or 6 degrees of warming over Australia. We've had 1.5, right? So that would really be a very tough. So fortunately, we seem to have dodged this high one and this very high one. We've been tracking more on this 2.7 degree one, and 2.7 degrees would still be a lot of warming, right? Because we've so far by 1.1, so to go to 2.7 is a lot of extra warming. And there's also a range on these. So this 2.7 is 2 to 3.6. There's uncertainty here due to uncertainties in the climate and in climate models and so forth that we can't. We need to factor in, but this is the average value. So the IPCC, so the current policies, and what I mean by current policies is what's actually legislated by countries. So sort of pre-Glasgow, you know, some countries like the European Union, you know, we're going to get to net zero by here, and by 2030 we're going to cut this. So this means legislated policies that are likely to happen result in warming of about 2.6 or 2.7 degrees. These are just three different groups that have estimated it. This is the UN group, and there are other groups that have made this estimate. So just three different estimations. If you look at, then you add in the 2030 commitments that were made, then that drops that by about 0.2 degree. So it does help, actually. But with those commitments, this means if those commitments were fully realised, so in other words, if a country has said we're going to drop by 50%, if it actually did that. So if they were fully realised, it dropped to 2.4 degrees. And then if you add in net zero promises, so countries that have said they're going to get to zero, so if they really do get to zero, if every country that pledges it actually got to zero, then you would see it does actually drag it down to probably less than 2 degrees. Okay. So if we all really did, if every single country that committed to going to actually did that, now there's a credibility gap here, of course, because in the scientific community there's a lot of scepticism that we would actually, the policies, that governments would actually truly go to zero. But if they do, so you can see the glimmer of hope here, that actually this, you know, that if governments live up to what they've promised them. And the last slide I showed was their progress at Glasgow. So that just shows what Glasgow did. And so here's what we were tracking in 2020 of the commitments that we had in 2020. Here were the commitments that we had prior to COP26, 2.4 degrees, and here's following COP 2.6 from the 2030 commitment. So you see there has been some progress on the extra commitments that you know, slowly pulling that down. And if you add the net zero promises that were made, and the new ones that were made, like Australia made a net zero one at Glasgow, effectively, you know, in the weeks before, then if governments really, truly do this, then we're pre-COP, it was 2, and post-COP pulls it down to 1.8. So it's not 1.5, right? So that's 1.5 is, in my opinion, it's out of reach, but it's pulling in the right direction. So despite all the hassles and so forth, you know, that there's a glimmer of hope that came out of, you know, we can't despair about this. There's a glimmer of hope that came out of COP26.
Well,
Yeah.
I mean, that Glasgow conference, we see the Chinese and the American president hugging and kissing each other. We've had no commitments at all what Russia... No, you're going to laugh. There's no commitment from Russia. They didn't know what they was going to do. No commitment from India and anywhere else. So to me, that's just a load of crap.
Actually,
India, no, I'm not going to go, but that's the way I look at it.
Look, I understand your cynicism.
Nothing from Russia.
But like India did make a commitment to zero by 2070.
Who?
So India made a commitment during.
Well, I didn't know nothing about Russia.
To actually. So China has made a commitment to zero by 2060. India has made a commitment to at 2070. So those countries have made commitments actually. Yeah.
I just had a question. You haven't mentioned tipping points or any of that sorts of
Right. So points of no return.
Yeah. So how reliable are these predictions?
Okay. So the answer is can catastrophic things happen even in like the 2 degrees? And the answer is yes, they can. But we, to the best of our knowledge, if we keep warming to sort of 2 or 3 degrees, we're not going to see really catastrophic changes in the, like, what was that film, you know, the morning after dark. So we don't expect those. There are tipping points for certain parts of the climate. Like for instance, our modelling shows that once we get to 2 degrees, even if we pull back below 2 degrees, then it might mean that the Greenland ice sheet will collapse. And once it collapses in a long time, it never recover, even if we were to get warming down. So we may have some irreversible changes like that, so affecting ice sheets. Other changes like from a haline circulation, I mean, you know, the basic circulation of the ocean, we don't expect these, certainly in the next century or so, these sudden catastrophic collapses, this kind of thing. So that's reassuring, I suppose. Yep.
International air travel. Questions in 2 parts. First of all, people may travel normally about 7 kilometres above the Earth's surface. Is that height chosen because it has less of an effect upon the environment of the atmosphere? And secondly, in the last 2 years, I know it's a very short period of time, scientifically, have there been any studies or any attempts to see that there have been significant improvements of the atmosphere?
Okay, so the answer is why they're quite so high, because the air resistance is less up there. Okay, so if you, especially on an international flight, it's just less able to push the aircraft through for 10,000 metres and lower. Aircraft, it's an interesting question of what effect aircraft have. Aircraft can affect climate, and the way they affect it is not just by the emissions from the aircraft, but they also cause contrast, like you can see clouds, like you see a contrast, and you see it like spread over the sky. So the question is, do contrasts have a warming effect on the climate? And the answer is yes, but it's very small. And also they inject water vapour into the very upper parts of the atmosphere. And remember I said water vapour normally just responds to temperature. If you inject it really high, it can have an effect. So right in the very, very upper atmosphere. But again, it's very small. Whether we've seen improvement in the air, we've seen reductions in improvements in air quality in some particular, so those aerosols are coming down. But greenhouse gas levels and so forth, well, as you see, they're like a record high level.
Yeah, my eyesight's not as good as it used to be, but to me the stars have looked brighter, especially Venus the other night. And I was just wondering if that's part of that is due to the lack of international air travel.
Look, there was an interesting, international air travel and its effect on the climate. It's an interesting thing. There was an experiment that was performed, and it was 9/11. So what happened with 9/11 is you have all these thousands of aircraft flying around the US, and then after 9/11 they shut them down for like 2 weeks or 3 weeks or whatever. And that was a perfect little laboratory, massive destruction. So it was a perfect little lab. People looking at it and seeing, okay, we can make direct measurements from satellites on how much greenhouse gas is coming up, without aircraft there. And so they do make a difference, but the difference is dwarfed by general industrial activity. Aircraft travel is important, but it's a small part.
I was just going to ask 2 quick questions. One is, what's the estimated range of sea level rise on those projections you put up?
Okay, so I didn't show that slide because I didn't have time to show everything. It's a good question. So in that sort of ultra business as usual SSP 8.5, the projection is about 1 metre of sea level rise by the end of the century. In the more moderate one that we might achieve, it's about 0.5 metre by the end of the century. Sea level is going up by about 3 centimetres a decade, but it's accelerating. The great unknown with sea level rise is the stability of ice sheets. So, for example, we showed really briefly the Larsen B ice shelf that collapsed in 2002. So an ice shelf's mostly it's not floating, right? And it also holds back glaciers behind it. So when you lose an ice shelf, you get the glaciers surge, and so you can get catastrophic sort of loss and collapse of ice shelves. And also you get this melting that takes place in melts, water melts through the cracks and then down to the bedrock, and then it can sort of lubricate the ice sheet to sort of break up. So if there's we think it's low risk, but there is some risk that it would be significantly higher than a metre by 2 or 3 metres, but it would require a collapse.
The other thing I was going to ask, you talked about actually sucking the greenhouse carbon dioxide out of the atmosphere. Is that just deep reforestation, or are there other technologies?
Okay, we don't have a technology. We don't have a technology, as far as I understand, that doesn't involve photosynthesis. So it's like a biochar or whatever, but the best technology we have for removing CO2 from the atmosphere is a tree. So unfortunately, since it's since it's 0.04%, it's very, very diffuse in the atmosphere, and so removing it chemically or whatever is extremely hard. It's actually quite a diffuse and trace.
I think there's something interesting they never talk about with climate change, and that's population. Because in the 70s we used to talk about population a lot. But that's hardly mentioned.
Yeah. Well, it's factored into the SSPs. So those socioeconomic pathways, they include population growth, economic growth, technology transfer, between developing countries and developed countries, and other factors like that. So it is in those assumptions, but it's implicit. So I'm done now. So I'll move to the summary. So I've known about the essentials of the greenhouse effect since the late 1800s. So we have known about it for a long time. We're very certain of it. It's certain that human greenhouse gas emissions have caused climate change, and we understand the contributions from individual gases, which I didn't really show. So changes that are a result of that, of course, we've detected rainfall patterns, temperature extremes, droughts, fire weather, heavy rainfall, snow cover, sea. It's almost easier to list what hasn't been affected. Marine heat waves, which I haven't talked about. Marine heat wave is like a heat wave on land, just sort of extra warmth in the ocean, and marine heat waves have been responsible for a lot of coral bleaching in recent decades, and the expectation, unfortunately, is that once we get to 2 degrees, that coral reefs will be 99% damaged. Further climate change is inevitable, but the magnitude is uncertain. The important thing is that climate change is very committing, because we talked about the CO2 lifetime, the heat that's warming the ocean, and ice sheet collapse, if it were to occur, is an irreversible collapse. To stabilise at 2 degrees is exceptionally challenging. I saw one of the commentators from COP26 saying 1.5 degree goal is on life support. So I think it's almost parked it, but it's like there's a glimmer there, and you just never know. To limit warming at or below 2 degrees, we need to halve by 2030, and that next decade is really crucial to net zero. Glasgow provided a modest step, but the next decade is critical. Future generations and ecosystems will inevitably have to adapt to a changed planet, and the question is how much. So I'll leave it at that. With one other thing, I'll leave you with the seasonal outlook. So this sort of when the focus. So, thanks a lot.
Any other questions for Robert?
Yeah, I've got another question. You seemed, I think you seem a little bit optimistic, more glass half full than empty on what we might be able to achieve.
Okay, yeah.
I don't know if that's true, but you seem that way. I'm a lot more sceptical, I think, and I'm just wondering whether we might have to use geoengineering type solutions.
Okay.
And what's your thoughts on?
Okay, so that's a really interesting question. I'm glad someone asked that. So what geoengineering means is actually deliberately trying to affect that radiation balance by the introduction of other things. So one form of geoengineering, remember I talked about how volcanoes, when they push aerosols into the stratosphere, they can last there for years. And Pinatubo cooled the planet very briefly by about half a degree. And that was from the reflection out from those aerosols. So there have been proposals to actually, using aircraft or whatever technology might be able to actually directly inject further particles into the stratosphere. So the stratosphere is, we live in what's called the troposphere, which is the bottom like 10 kilometres of the atmosphere, and that's where all the weather occurs. If you go above that, then it's a very, very stable layer, and there's very little weather in the stratosphere. And things that are there don't rain out, so they can stay there for a very long time. So Pinatubo affected things for like 2 years. And so the thought is you can inject reflective particles or something into the stratosphere that will stay there for a long time, and they will cool the planet. So IPCC doesn't talk much about geoengineering, and but it is proposed from time to time. So geoengineering, there are risks with geoengineering, of course, and the risks are that, remember I showed you that rainfall patterns get changed with global warming. So if you were to inject sulfates or something into the stratosphere, then you will also move around rainfall patterns. We don't know how, but research really hasn't been done exactly how they do it. So it's sort of there'll be winners and losers out of it. And so for that reason, there's like some hesitancy among, some areas, policy areas, and perhaps even scientific areas to explore that option. But it's really a question of, ultimately, I think it's a debate to have, actually. And I think it's a question then of risk. Right? If we warm up a lot, there's risk associated with that. If we start geoengineering, then there's a risk associated with that. That's society needs to balance those risks, which is the worst one. Me personally, there are times I feel we should, or at least investigate it, seriously investigate it, because I don't think I think these policies won't be fully fulfilled if they want to meet their 2030.
There are no international agreements.
Yes, it is. I mean,
but it's an open question. I mean, we put the question to the debate. It's not a scientific yes or no. That's the ultimate policy question. I mean, there are other thoughts, like people talk about spreading iron filings in the ocean to sort of pull carbon dioxide out of the air from sort of plankton fertilisation and so forth. So there are some other ideas that you could call that geoengineering.
Brightening clouds is another possibility.
You see clouds, so I've heard talk about if you go into the Pacific where there's low decks of clouds, like that cover a quarter of the Pacific, like a huge part of the planet. You have ships travel backwards and forwards with soot coming out of their funnels, and they affect the cloud lifetime, and they make the clouds brighter and more reflective. So these things could be tried, but there's also a question of timescale and commitment. You see, say we go that path. To start, we don't avoid ocean acidification, that just continues, which I haven't talked about. That's a bad thing to have. But secondly, it's a question of if carbon dioxide keeps building up and you put stuff in the stratosphere, it'll help you only as long as you put it there. You sort of mask more and more latent warming. And if ever you pull that off, of course, bang, the climate explodes again. So there's no substitute for getting carbon to zero. Right? This might give you 2 more decades, though.
Yeah, there would like be a holding pattern for governments to reduce their emissions without affecting society too much.
I mean, no one's mentioned methane. Methane is also a good thing. See, another way we could tackle methane. But methane has a lifetime of about 12 years. So actually, methane, you've got to get methane under control. The carbon dioxide, because it keeps accumulating, has to be tackled. If you're ever to stabilise the climate, you've got to get those emissions to zero.
Just a something for you.
Oh, thank you very much.
So thank you very much for coming down.
Hi everyone, my name's Mark Stevens and I'm presenting Sky for the month of November 2021. A little bit rusty, I've been doing this voiceover for a while, so if I go silent it means I'm waiting for it to talk itself. A couple of things happening for November and December. If I had realised we weren't meeting in December I probably would have added a few other things, but for those who want to find out, you can look at Astronomy 2021 yourself. You notice there's a couple of comets there at the moment. You've got Comet Tuttle, you've got Comet Borrelly down here, and Comet to your rest. I'll just point out, particularly for the newer members, that these are objects around about 9th, 10th and 11th magnitude, so they're not naked eye objects. In addition to that, we've got a couple of meteor showers, and I've been practicing this one all day. The Alpha Monocerotids shower occurring between the 15th and the 25th of the 11th, and the 22nd of the 11th is the peak time when you'll see most the feedback. You've got the Phoenicians, meteor shower, 28th to the 11th to the 9th to the 12th, peaking on the 2nd, and I believe that is one for the early morning people, those who like to get up and run around after midnight. And down the bottom you've got the Geminids meteor shower between the 4th of the 12th and the 20th of the 12th. A little bit more about them later on. Mercury in superior conjunction. Particularly for the newer members, that means it's on the far side of the sun from us. It's in conjunction with the sun, but it's the other side. It has two conjunctions. As it runs around the sun again, it'll come between Earth and the sun, and that's its inferior conjunction. So it's a fair way away at the moment, but it's a fast little planet, so 44 days it'll be back in inferior conjunction. Full moon occurring on the 19th. It's probably not going to really help those who are looking for the comets. And for those that are really keen, DP stands for dwarf planet. Ceres, which is the largest in the asteroid belt, is in opposition on the 27th. Looking at the night sky for November, looking to the south. Not a great deal. Something worth noting though is Orion is now starting to pop up over the horizon for those who are wanting to photograph the Orion Nebula, which shows up pretty well for those with a camera, or even just indeed see it. You've got Large Magellanic Cloud complete with its Tarantula Nebula. That's another popular one with the astrophotography group. And the amazing thing, if you actually get that on your camera, you're looking at an object that is not only in, it's not in our galaxy, it's actually in another galaxy outside of our own. As far as globular clusters go, Omega Centauri is a little bit low. It's down here at the moment. So you've got 47 Tucana up here, which is quite easy to find. It will show up in the finder scope of most telescopes, so centre it and then look at it through your telescope. And you've got a globular cluster there. Looking to the north, probably the main feature on the northern sky is the Andromeda Galaxy here. This time of the year it's actually above the southern horizon and can be seen. The only problem with seeing it from here is we've got a couple of horrible trees in the way. We've also got the lights of Melbourne ahead causing light pollution, so really not going to be very easy to find it from here. If you want to have a look at it, you need to go somewhere with a good northern horizon and no light pollution. It's fair size, it's quite a large object, I have been told that if you get nice dark skies, you can actually see it with the naked eye, but obviously the light from these things come from a fair way away, so they're not all that bright. Okay, and I was having a look at another chart earlier, and you've got this little circlet of Pisces here. This star here is actually a carbon star, and what that is, as we know, stars fuse hydrogen to form helium, giving off their radiation and heat and light, that sort of stuff. A carbon star has consumed all its hydrogen, it's probably burned all its helium, and it's now fusing carbon atoms to produce iron and heavier elements. Essentially that's how all the elements were formed, so everything in your body other than hydrogen is effectively stardust. What are the planets up to? Well, who wants to see Mercury this month? Well, you're not going to be able to, because it's actually the other side of the sun. It's in superior conjunction on the 29th to the 11th, which means it's far side of the sun, so it's very low on the eastern morning horizon. So probably disappear in twilight or dawn. Venus, who saw that big bright one up there on the way in tonight? That's Venus, pretty obvious. Venus is actually heading towards, well, it's actually reached its maximum elongation. That basically means it's as far away from the sun as it gets. As it circles the sun, both Venus and Mercury are closer to the sun. So we're standing on the top of the Earth and we're watching them, and they go around the sun like this. So wherever the sun goes, these planets go with it. So as the sun sits below our horizon, we're waiting to see them when they're still up, when they're circling. And they do that twice. Once maximum elongation east and west. One is in the evening sky and one is in the morning sky. So at the moment, Venus is just through its maximum elongation east. It's actually got, I think it's called east, getting confused now. And what will happen now is it will start to, it's actually coming towards us, so it'll head towards inferior conjunction between us and the sun. And what will happen is it'll get closer to the sun, and so it'll get lower in the sky. So now's the time for those who really want to look at Venus to get out there and have a look. Earth, nothing really spectacular in Earth at the moment, except we're still looking for a summer and spring, and I'm not going to, after the talk tonight, I think I'll just skip past Earth. It's obviously got a few more issues. Moving on to Mars. Mars has moved through its conjunction with the Sun. Now, being an outer planet, it has a conjunction and an opposition. It doesn't have the two conjunctions like the inner ones. So, essentially, it is the other side of the Sun. Given it's 1.5 astronomical units from the Sun, and we're 1 astronomical unit from the Sun, it's 2.5 astronomical units away. Astronomical unit being the distance from the Earth to the Sun. So a fair way away, not in a very good position to view, and over the next, towards the end of the month, it will rise again in the eastern morning sky. So another one for the early risers. Jupiter and Saturn, I'll include them together because they're not very far apart. And at the moment, you've got Venus, Saturn and Jupiter. And really you keep going, you've got Neptune and Uranus all up there at the moment. All, well, most of them visible with the naked eye, but the last two they aren't. But they're not that hard to find at the moment. Now, Saturn has just passed through the point known as its eastern quadranture, which essentially means it forms a 90-degree angle between Earth to the Sun out to Saturn is 90 degrees. And the best part of that is it gives you the maximum shadow on the rings, and so you can see the planet casting its shadow on the rings gives it a terrific 3D effect through a telescope. Certainly worth looking at that. You'll still have the shadows on the rings there at the moment. Uranus, still in Aries, going to be there until about 2025, I believe. It's rising a little earlier than just after sunset now. It's a good object to have a go at, mainly because it's right on the cusp between you can or can't see it. So if you're in a really dark sky position and you've got the eyes of a 10-year-old, you'll probably be able to just see it. Anyone older than that, get a telescope. Alright, and Neptune, get a telescope anyway, and probably for most people a go-to scope. And when you actually look where it is at the moment, it's got 3 little dots. I actually put a picture of it on Facebook about 2 weeks ago, and I actually checked an app to make sure I had the right one. Quite clearly see the colour in both Uranus and Neptune, but there's not many other features. Appearance of the planets. Alright, Venus, as you can see, is quite large there. The reason for that is it's heading towards, it's just come through its maximum elongation, but it is heading in towards inferior conjunction, which essentially means it's getting closer to Earth. Because it's getting closer to it, its apparent size is increasing. And when it gets into inferior conjunction, it's only 0.3 of an astronomical unit away. It's the closest planet, or any planet, comes to Earth itself. But because it is moving between us and the Sun, we're looking at the back of it, which is unlit. But what you will see, because it is quite large, is you will see this crescent. All right. Mercury is the same, but you'll note the light is on the other side. And that's because Mercury is heading towards superior conjunction. So it's gone around the other side of the Sun. We're now looking more at the face. So we see more of the face. And because it's effectively on that side of the Sun and Venus is on that side, the side of the slit is slightly different. It's a fairly small object. It is visible to the naked eye when it cooperates and appears above the horizon. But otherwise, at the moment, given it's heading towards superior conjunction, really not a good time to watch it. They put a picture of Mars there, but Mars is about as far away from Earth as it can get. So about this time next year, it'll be near opposition or in opposition. So another 12 months before Mars is worth looking at. Saturn still has the rings tilted towards us. 2025 will actually pass through what's known as the ring plane. Because the rings stay orientated to the Sun, you've got your Sun and the rings. Like a gyroscope, they stay orientated the same way all the time. So when it's side onto the Sun and we pass through it, we'll pass through what's known as the ring plane, and all we'll see is the planet. We won't see the ring system. That happens in 2025. So at the moment, we're looking at it from above. Once we go through the ring plane, we'll be over here and we'll be looking at it from below. Telescopes confuse the issue because they can flick the images. Jupiter, why it's up and visible, always fairly special and specky. Main things you're looking for are these bands. Suitable size telescope, you might see the red spot. And obviously the full moons and their various configurations, which change all the time. And some of the really keen ones, they like to check out the moon shadows as they pass in front of it. Uranus and Neptune, as I said, fairly small. Main thing you're looking at there is the colour of the discs. There's not a lot of features, even through a big telescope on these things. If you can spot some of the moons of Uranus, you'll notice they tend to go in the vertical. That's because Uranus fell over on the way to the solar system, and it runs around the place on its slide. Other stuff at the moment, we've got 4 comets. Comet Borrelly, I assume it's Borrelly or Borrelly, not really sure. It's visible throughout the night in Greece. So, I'll go back a few. Okay, there's Greece there. So, next to Capricorn and Aquarius, and the sculptor. So, that's where it is. It is expected to brighten from 11th to 9th magnitude. The human eye is capable of seeing about 5th magnitude, so you will need a telescope to see it. But as I said, it is visible throughout the night, so it's worth having a look for. Comet Faye, I've included that there. Comet phase rises mid-evening in Monoceros. It has gone through perihelion, in other words, it's heading back out to the Oort cloud, and it's currently 11th magnitude and fading. This is another one I have to practice. Comet Churyumov-Gerasimenko, I think that's right. It reached perihelion in early November and will remain around 9th magnitude. So you've got two comets out there at the moment that are relatively bright for comets at 9th magnitude. However, it's a morning object found in Gemini, and mid-month moves into Cancer, where it will remain. So for the new members, the constellations you want to start learning and getting used to are probably the ones of the zodiac. So not that they're all that bright and easy to spot. And the last one, Comet Cayley, visible from early evening in Aquarius in December. It's more into December. I'll put it here because there is no reading for it. And it'll brighten to about 10th magnitude as it moves into Pisces. 3 meteor showers. The northern Taurids. I think last month we had the southern Taurids. Well, the fact they're called Taurids, it basically means the place where you look for them to come from is Taurus. So find Aldebaran and you pretty well got Taurus, and that's probably where most of them are going to come from. Active from the 20th to the 10th to the 10th to the 12th, peaking around the 12th. These are fairly large, slow-moving fireballs. Not a lot, only about 5 per hour, they reckon. And they're associated with Comet Encke, which we've been mentioning for the last couple of months. So, this Comet Encke has been around earlier this year. There might be a few more because we go through the tail. The Leonids, they come from Leo, obviously, and they're active from the 6th to the 30th, with a peak of about 15 meteors per hour around the 18th to the 11th, so tomorrow night. And Leo rises about midnight, so another one for those night owls. And that one, active 15th to the 11th to 25th to the 11th, peaking around the 21st, and unfortunately they're best viewed after midnight. Problem with both the last two is because of the full moon, which occurs I think tomorrow night, they can be drowned out a little bit.
Can't read it, Mark. What's the name of it?
Basic astronomy, as Peter put in his early MPAS telescope learning day, this Saturday, 20th of November, starting at 4 p.m. So it's members only event this year. Normally we do run it as an open event, but we've kept remaining events this year to members only. So bring your telescope. Best way to learn how to use it is to play with it. And there'll be someone here who should be able to pretty much help you irrespective of what telescope you've got. Fred's just busting to help everyone with the dog.
They're picking on my phone, I didn't say nothing.
Alright, it will include a basic astronomy talk, give you a bit of an idea of what sort of things to hunt for. A bunning style barbecue, rather than an elaborate barbecue. And obviously the opportunity to play with the telescope, and that red showed up better when it wasn't on that screen. Subject still to the Chief Health Officer requirements to QR code in, wear a mask inside, you don't have to outside, be fully vaccinated and observe higher COVID hygiene rules. And as usual, tonight's information was provided by Astronomy 2021 by Wallace Gores and Northfield. And do we have unclaimed copies of 2022 one? Simon? Oh, he was there. 2022 is available out there, so speak to Simon or someone else in the merchandise area there if you are interested in purchasing a copy of this magazine for next year. They are very, very handy. Any questions? Any answers?
And now we come to the details of the competition outcome that we ran in August as part of National Science Week to give away 5 meteorites as part of a nationwide competition of school-age children. As shown on this slide here, there's a couple of well-known meteorite falls shown here, particularly the right-hand one from Peekskill near New York in the USA that demolished that poor young lady's car. Well, during Science Week we had the competition running for just under 2 weeks, and in that time we ended up with 165 valid entries across Australia once we took out any duplicate entries that happened to be in there. It was open to all primary and secondary school students as well, and the aim of the competition was for them to estimate how many meteors, actually the size of a grain of sand or larger, impact the Earth in a given day, so in other words across the world. And the winner was going to be taken as the so-called wisdom of the crowd method, so not necessarily the correct answer or the best known answer, but the one that's actually determined by the students themselves. And the beauty of this kind of competition is that you never really know the answer until you've got all the responses in from the survey from everyone, because the wisdom of the crowd method can vary a little bit over time. So if we look here, these couple of graphs, the first one sort of shows the distribution by age, and as you see the most popular ages were around the 11, 12, 13-year-old mark, so you're looking at late primary school, early high school over this period of time. And on the right hand side is the distribution of the actual answers received in terms of their estimate of the number of meteors across the world in any given day. And one shown there under the by the red arrow is one that is very probably due to people just relying on a Google search, finding that NASA indicates about 100 tonnes a day come in, and it's 2 because it's log base 10 shown on this particular graph, which is 2 for 100. And many of the students would not have realised that what NASA was giving them was a mass in terms of tonnes rather than actually a count of the number of meteors actually coming in per day. The other one that's a little bit of a mystery is why 10 to the power of 8 is such a large answer as well, and not entirely sure why that would be. Sounds very unusual, so I suspect it's probably a unit of measure thing as well. Now, as I said before, we had to illuminate a handful of duplicates from the same student where they entered more than once, and in this particular case when that happened we only kept the most recent answer, on the assumption that they realised that they may have made a mistake the first time, and so we're having a go with a second guess. So we always kept the more recent entry in that particular case. Now, when considering a competition like this, you have to remember that the Earth is approximately 2/3 of water, so it's not just the meteors that are seen over your particular location or over your country as well, but it's also the meteors that would not be seen by you, that would fall in the world's oceans and seas as well, and lakes and everything else. Now, impacts from bodies from space can come from any direction at any time of the day and night, so it's not just a nighttime thing, it's also a daytime thing as well. Now, sand, interestingly, does have a formal definition, and indeed a Google search will show this fairly readily. And the lowest size of a particle of sand is actually considered to be 1/16 of a millimetre diameter. So 1/32 of a millimetre in radius. Anything below that is considered silt rather than sand. And because the competition is looking at anything the size of a grain of sand or larger, it's therefore 1/16 of a millimetre diameter or larger coming in. Now, the smallest guess that we had from anyone was there's only 1 meteor a day anywhere seen in the world, which is obviously an extreme outlier. And the other one that was also by far an extreme outlier was 700 sextillion per day, which sort of equates to the equivalent of 2 Mount Everest full of sand falling from the sky in any day, which would probably be very, very noticeable if in fact it did occur. Now, the wisdom of the crowd method used in this case was the median, so as to exclude those extreme outliers. And based on that, the median value of all the 165 entries was indeed 100,000 meteors a day, and a few students actually guessed that one correctly. Now, that may be the answer that is used for the basis of winning, but what is actually the true answer? What is actually the accurate answer best known to science? And that can be summarised in these 2 references shown on the screen here by Bland and Artemeva. Bland is from Imperial College in London, and Artemeva is from the Russian Academy of Science, and they've done quite a lot of work in this area of meteors and impacts on the Earth of various sizes, from huge bolides coming in from space, such as say the one that wiped out the dinosaurs 65 million years ago, right down to tiny fragments coming in from space as well. And they've done a lot of work not only themselves, but also pulling in the results of other researchers who've been looking in this field. And particularly at the low end of the thing, with small grains coming in, it's a matter of relying on photographic evidence. So in other words, there are many meteor networks around the world whereby they photograph the sky at all times of the day or night, or indeed use radio techniques even during the daytime to detect incoming meteors being detected. And they have pulled those results together to try and find relationships with the number that are coming in for a given size, and they've actually done very well in that regard. Now, one of the results is shown on this slide, which shows a graph on the right hand side, and indicated along the bottom on the x-axis is the mass of the object coming in from space, the meteoroid coming in from space. And it ranges on the right hand side shown there to from about 10 to the 15, 10 to the 16 kilograms. So in other words, that's 1 followed by 15 or 16 zeros, which would be absolutely huge. Way over on the left hand side, getting on for just a few grams only. And the y-axis, the vertical axis shown there, is the number of meteors of that size or larger. So in other words, it's a cumulative number of objects shown on that y-axis, the vertical axis. And what I've done on this graph is I've extended it with the brown line that goes off to the left hand side, fitted to their particular data, and moved the vertical axis to the point corresponding to what the mass of a sand grain is, which is the far brown vertical axis shown there. And as you see, it crosses there just above the 10 to the power of 8 of them per year. And how that's actually determined is if we follow the numbers 1, 2, 3, 4, 5 in yellow shown on the slide. First of all, they've determined the formula for that brown line, which takes from objects 1 kilogram and less. They're fitted by that formula log base 10 of n, where n is the number of objects of that size or bigger, equals minus 0.492 log base 10 of m, where m is their mass in kilograms, plus 3.646. So that only applies if it's 1 kilogram or lighter. And if it's larger, then other formulae are actually applying as shown in those previous 2 papers. Now, because we know the definition of sand is 1/32 of a millimetre in radius, we make a good physics assumption that every particle of sand is approximately a sphere. and that it's going to be made of something equivalent to silicate, or in other words sand, which has a density of 2.6475 grams per cubic centimetre. So we can then calculate the volume, V, and that then enables the mass of a grain of sand to be found, because the volume of a grain of sand is equal to the volume of that sphere, which is 4/3 times the number pi, which is approximately 3.14159, times the radius, which in this particular case is 1/32 of a millimetre, to the power of 3. And that will give a volume, and then we put it into the formula based on the density times the volume. It gives the mass of a grain of sand to be approximately 3.38 by 10 to the minus 10 of a kilogram, so a really small mass. Then over at number 4 on the slide, you can therefore see that if you plug that number for the mass of a grain of sand into the log formula in number 1, it gives log base 10 of the number of grains of that size or larger, as coming in at 8.31, which would be where the brown slanted line actually intersects the vertical axis over on the left, and that comes in at just over 2 by 10 to the power of 8 objects per year. So in other words, that's 2 followed by 8 zeros, but that's in a year. So then if we go over to yellow number 5, if that was the number in a year, then if we divide that by 365.25 days in a year, that gives you the number of objects of that size or larger, the size of a grain of sand or larger, that are striking the Earth every day. And in this particular case, it comes out at over 500,000, so 553,000 objects a day, based on the best available observational evidence. So the answer as far as the competition went, based on the submitted answers from the students across Australia, was 100,000 per day, and the literature assessment is 553,000 of them per day. Now, it's interesting to note that the number of entries actually submitted varies a lot by state. The most popular state was Victoria, followed by New South Wales, and both of those were the two that were in lockdown at the time due to COVID. So obviously a lot of students there are working from home, and obviously found time to submit an answer to the National Science Week competition. And vastly outdid the next states. The next best one was Western Australia, followed by the ACT, South Australia, Tasmania, and we didn't actually get any entries from Queensland or Northern Territory at this particular time. Now, the winners actually of the competition are shown there, and just purely by coincidence, they all came from Victoria. They just happened to be the closest ones to the answer. So we had Harry Williams from Frankston, Kiara and Kian Pinto, brother and sister from Glen Waverley, Will Seedy from Vermont, and also Antonia Zabel from Brunswick North. And congratulations to those winners, who are now the proud owner of a meteorite from Argentina. Right, now on to the educational videos for today. We first of all have one detailing about the earthquake that hit Victoria back on September the 22nd, being the largest, or about the largest, that has ever been recorded in Victoria. Doesn't mean that there haven't been larger ones, because indeed Port Phillip Bay was indeed formed by the movement of the earth going downwards, then filling up with water. So we obviously had much larger movements in the past, but this is just recorded information. We'll follow that after that by a video by the National Security Space Institute in the United States, talking about the space environment near to Earth. So this is the environment that is not only from particles coming in from the sun that give rise to the aurora australis that we've seen in the sky, particularly in the last week or two. But also the other effects that can occur in space that also have, in some cases, very severe impact on man-made satellites orbiting in low Earth orbit, which they refer to as LEO, or at geostationary orbit, which is much higher up away from the Earth, which they refer to as GEO in this particular video. After that, we'll close before closing the meeting with a 5-year time lapse using different regions of the spectrum. This is taken by the orbiting Goddard Solar Dynamics Observatory from NASA, and collating together 5 years worth of the sun in just a couple of minutes. And that will also be shown in the background with audio from Christian Telford of Power and Progress, so hopefully you enjoy that.
Hi, my name is Ross Cayley and I'm a senior geologist who works for the Geological Survey of Victoria, which is part of the Department of Jobs, Precincts and Regions. Like many Victorians, I felt this morning's earthquake. First there was a rumble and then came a wobble. The rumble was from the P wave. This is a pressure wave that travels outwards from the location of the earthquake like a sound wave in the rock. The wobble was from the S wave or shear wave, which travels from that same location but more slowly, so that it takes slightly longer to arrive at the places where it is felt. The time difference of several seconds between the two wave arrivals immediately indicated to me that the earthquake epicentre must be located about 100 kilometres away from where I experienced it in Melbourne.
Hi, my name's Tim Rawling. I used to work with Ross, but now I work at Auscope, which is an organisation that puts sensors for researchers around Australia to monitor geological changes like earthquakes. I also felt the earthquake this morning while I was on a teleconference to a colleague of ours, Dr. Steve Hill, who's in Canberra. When the quake hit, I was pretty excited too, like geologists are by these things. And about a minute later, Steve felt it as well in Canberra. So like Ross, we quickly knew it was a very big event. And we thought it was probably located somewhere between here and Canberra, but probably a little bit closer to Melbourne.
Using seismographs, Geoscience Australia have determined that the earthquake epicentre was near Matlock, east of Melbourne, at a depth of approximately 10 kilometres. Early analysis suggests that, with a magnitude of about 5.9, this earthquake is one of the biggest onshore earthquakes ever recorded in Victoria. Any earthquake of this size is usually followed by a number of smaller aftershocks. So it's no surprise that there's been at least 6 of these so far. The aftershocks are expected to diminish in frequency and intensity with time.
I have a small seismometer in my study at home and quickly pulled up the seismograph from the event. It was really quite exciting, as this has been operating for years and mostly just records my teenage boys banging doors.
Although newsworthy and a really memorable event, this morning's earthquake is still relatively small by global standards. And today's earthquake is consistent with previous earthquakes recorded in Victoria, for example, the magnitude 5.2 Maui earthquake, which occurred in 2012. And the magnitude of today's earthquake is what geoscientists expect, based on what we know about the geology of Victoria. But many people are probably wondering why earthquakes occur in Victoria at all. Australia, including Victoria, lies in the middle of a relatively stable geological plate. We are mostly protected from the larger earthquakes that occur along the active plate boundaries. Our fortunate geology means that today's earthquake is amongst the larger earthquakes that geoscientists consider likely to occur in Victoria. Victoria does experience occasional earthquakes though, and this is because geology is all interconnected. Our geology is connected to other places, and stress generated by geological processes operating in those other places, even places located thousands of kilometres away, can be transferred into Victoria to cause our earthquakes, and this is exactly what we think is happening. The other place most relevant to Victoria's earthquake story is the Australian plate boundary, and the closest part of the Australian plate boundary to Victoria is New Zealand. New Zealand sits on the boundary between the Australian and Pacific plates, and these are currently colliding against each other. The picturesque New Zealand Alps are the result of that ongoing collision. Some of the compressive stress from that active New Zealand plate boundary collision is being transmitted west through the crust beneath the Tasman Sea and into southeast Australia. Geoscientists can even measure this force and its direction in our own geology. It is this stress that causes the smaller earthquakes in Victoria, and this means that Victoria's evolving geological history is intimately tied to what's happening in New Zealand. Earthquakes in Victoria occur when small segments of pre-existing natural fault lines reactivate in response to this stress. Today, a small segment of an ancient fault, a fault formed over 400 million years ago when much of Victoria was first uplifted out of an ancient ocean, appears to have reactivated to cause today's earthquake. Geologists have previously mapped this fault and we named it the Governor Fault. It's a large complex structure that extends from near Echuca and the Murray River in northern Victoria to near the Gippsland Lakes in the south. It passes through the heart of the Victorian Alps. Geoscientists have imaged this fault and shown it to continue to below 35 kilometres depth in the Earth's crust. It likely extends much deeper than that. It was already considered as a prime candidate to be locally reactivated in the current Victorian stress field. However, it is not the only ancient fault line in the state that can experience earthquakes today. Victorian geologists have mapped hundreds of other such faults across the full width of Victoria, and there will be other faults that we don't yet know about as well. And this is why research into understanding Victoria's geology is ongoing.
Indeed, we know that there have been some very significant earthquakes in Victoria. A large fault scarp formed near Echuca between 25,000 and 70,000 years ago, dammed up the entire Murray River and formed the then huge Barmer Lakes. Based on the size of this surface rupture, this event was estimated to be larger than a magnitude 7. Imagine the impact of an event that size in Victoria today, based on what we felt with the earthquake earlier.
It is not possible to predict the precise time or location of any given earthquake, or exactly which fault or which bit of a fault might reactivate next. However, it is possible to use the landscape to predict where more active faults lie, and it is no surprise to geologists that today's earthquake occurred in a very mountainous part of Victoria. Mountain uplift is a direct result of the fault reactivations that also cause earthquakes. Uplift of mountains in Victoria, particularly the Alps and the Strzelecki Ranges in Victoria's east, is testament to the cumulative effect of lots of small fault segment reactivations, which over several million years would have resulted in lots of small to medium-sized earthquakes distributed all over central and eastern Victoria. Today's earthquake is just a continuation of that long, ongoing natural process. The Geological Survey of Victoria has long known about the earthquake potential of our geology, so we're undertaking active research together with interstate and national research agencies. We want to better understand the stresses in the earth and to make sure risks from earthquake events can be identified and managed as effectively as possible. If you'd like to know a little bit more about the Geological Survey of Victoria's work and about the effects of earthquakes in the landscape, please view the short film entitled Geoscience Beneath the Australian Alps. It's available on the department's YouTube channel.
Hello and welcome. In this educational aid, we are going to cover the space environment and its effect on spacecraft. The space environment effects can be grouped into 6 categories: vacuum, neutral, plasma, radiation, micrometeoroid, orbital debris, and scintillation. And depending upon which orbital regime your spacecraft is operating, the impacts of these effects on your space mission can range from negligible to mission-threatening. This educational aid explores the space environment effects depending upon orbit and how each of the subsystems can react to the space environment. The vacuum environment. The vacuum environment is characterized by the lack of atmosphere like we have on Earth and very low pressure. As we detail this environment, we will look at how the near vacuum of space and lack of pressure, the resultant outgassing, and UV degradation affect spacecraft. Atmospheric pressure is about 10 orders of magnitude less at orbital altitudes such as 350 kilometers than on the surface of the Earth. This significantly reduced pressure affects structures, payload, and thermal control subsystems. The lack of pressure can affect structure subsystems because of outgassing. Outgassing is the loss of material mass as a result of volatile chemicals inside the material surface escaping into the vacuum environment or onto the spacecraft itself, leading to contamination. The vacuum environment also presents challenges in thermal control. Without the presence of an atmosphere, the spacecraft primarily uses radiation to aid in heat transfer for cooling. Depending upon the material properties used and contamination buildup due to outgassing, cooling can be further hindered. Outgassing is one of the greatest sources of contamination on the spacecraft. An example of outgassing on the surface of the Earth is the odor or smell given off by a rubber tire. In the vacuum environment, outgassed material escapes in random directions. Depending on where these escape particles go, the buildup of material can degrade solar arrays, fog up sensors, and alter thermal properties of structures and other subsystems. Additionally, in the vacuum environment, we need to take into account ultraviolet degradation. The Earth's atmosphere protects us from most of the harmful radiation from the sun. However, in space, our spacecraft aren't so lucky. As a result, ultraviolet radiation emitted by the sun adversely affects many materials on satellites. This radiation interacts with many surfaces on the spacecraft and over time can change the molecular composition of many materials, specifically by the removing of oxygen molecules from materials. As a result, the thermal control subsystem may not operate as desired, optics can be degraded, and solar rays may not be as efficient. The neutral environment. The neutral environment deals with the Earth's atmosphere and how it reacts with the sun's energy and interacts with the Earth's electrical and magnetic forces. Because we are primarily interested in how the neutral environment affects spacecraft, we will focus on the area of the atmosphere from 100 kilometers up to 1,000 kilometers. So essentially, the thermosphere and the exosphere portions of the Earth's atmosphere. Again, we just talked about the vacuum environment, but it is important to note that there's still a little bit of atmosphere left, and this little bit has an effect on spacecraft. From 100 kilometers to around 650 kilometers, molecular oxygen is the most prevalent component in this region of the atmosphere. However, solar energy breaks down molecular oxygen quickly and forms atomic oxygen. The solar cycle will affect how much atomic oxygen is present. During the minimums of solar cycle, there is less atomic oxygen than during solar maximum. But no matter where we are in the solar cycle, atomic oxygen is present. Atomic oxygen, or the neutral environment, affects spacecraft in several ways. We will discuss three. First, atomic oxygen reacts to various materials, leading to erosion, oxidation, and general degradation of material properties. For spacecraft with shorter mission life, this tends not to be too great of an issue. But for spacecraft with longer mission life, this needs to be considered to ensure the satellite will work throughout the full mission lifetime. The next effect is drag. Drag is caused by the density of all the constituents in the LEO atmosphere. From 100 kilometers to 650 kilometers, atomic oxygen is the primary constituent in this range. The drag experienced by the spacecraft is much lower than that experienced by a plane or a car at or near the surface of the Earth. But it has a significant effect on the spacecraft and its orbit. Drag acts as a small series of retrograde thruster firings by the spacecraft, robbing the spacecraft of energy. As the spacecraft orbits the Earth, the spacecraft's apogee gets smaller and smaller, eventually circulating elliptical orbits and eventually reducing the orbital altitude and energy. Finally, it can bring the spacecraft into earlier reentry. However, drag can be overcome by orbit prograde thruster firings, restoring energy to the orbit. The last effect is not well understood, but is a factor of the neutral environment. This effect is spacecraft glow. Some external spacecraft material, when they react with the neutral environment, can glow. Spacecraft glow does not seem to harm the spacecraft, but depending on the mission of the satellite, such as observations, spacecraft glow can have an adverse effect to the mission of the satellite. The plasma environment. Plasma environment affects orbits from LEO all the way out to GEO. The plasma environment is characterized by the charged particles, specifically electrons and ions, and their interaction with the spacecraft. In space, plasma is formed in two ways. First, when atoms are excited by solar charged particles, releasing electrons, creating ions. This process is called ionization. Second, by charged particles from the sun that are trapped by the Earth's magnetic fields, forming the Van Allen radiation belts. In both cases, electrons and ions interact with the surface of the spacecraft, causing an electrical charge buildup, or a potential difference. The rate of potential difference buildup is dependent upon several factors. Some factors include orbital altitude, inclination, and spacecraft material. However, as the potential difference increases, the charge needs to equalize. It does so by arcing. Arcing is an electrical discharge. Depending upon the current and voltage, the arcing can cause minor issues such as sputtering or pitting of surface materials to causing permanent damage to electronic components. The radiation environment. The radiation environment is characterized by highly energetic particles reacting with the spacecraft. These energetic particles are either charged particles, such as electrons and protons, or uncharged particles like neutrons, such as gamma rays and X-rays. These charged particles are much more energetic than particles in the plasma environment by orders of mega electronic volts. Unlike the plasma environment, these energetic particles can pass through surface material of the spacecraft, affecting the internal components. The effects on the spacecraft include degradation of component material, decreased solar ray power output, solar ray degradation, and single event upset. Single event upset is the flipping of a bit of data from a 1 to a 0, or from 0 to 1 that is received by the spacecraft or any of its electronic components. This can result in missed or fraudulent commands being interpreted by the spacecraft. Concerning the radiation environment, we are going to cover 3 sources of charged particle radiation and their effect on spacecraft. They are the trapped radiation in the Van Allen radiation belts, solar particle events coming from our sun, and galactic cosmic rays coming from nova or supernova explosions from outside our solar system. The Van Allen radiation belts are 2 regions of increased charged particle radiation. The exact bounds of these belts vary due to fluctuations of the Earth's magnetosphere, which compress and move the belts due to solar activity. The lower belt starts at 500 kilometers and extends to 6,000 kilometers. However, this lower belt has an area called the South Atlantic Anomaly that dips down to 200 kilometers over the Southern Atlantic Ocean. The South Atlantic Anomaly affects virtually every satellite in LEO. The outer belt ranges from 13,000 kilometers to 60,000 kilometers, affecting a large portion of the MEO belt and all of the GEO belt. Solar particle events are solar flares, solar storms, and coronal mass ejections from the sun. These events send high volumes of particles in all directions. Occasionally, those directional events intersect the Earth's trajectory. When that occurs, they cause problems. These events tend to last for a couple hours, but their effects can linger for weeks. The Earth's magnetosphere helps protect the Earth from some of the harmful effects of these storms. However, only some satellites are protected by the magnetosphere, depending on their orbital altitude and inclination. The lower the altitude and inclination, the more likely the satellite will be protected. Again, as mentioned in regards to the Van Allen radiation belts, solar storms can compress the Earth's magnetosphere and expose the geobelt to these storms and their harmful effects. Galactic cosmic rays are comprised of hydrogen, helium, and heavier ions. The magnetosphere does tend to protect some orbits, as with the solar particle events, as mentioned earlier. But these heavy, high-energy galactic cosmic rays can penetrate the magnetosphere, spacecraft structures, and penetrate below the Earth's surface. However, the main effect of galactic cosmic rays are single-event upsets in the spacecraft. The micrometeoroid orbital debris environment. The micrometeoroid orbital debris environment affects all of our orbital regimes to one degree or another, but the threat of orbital debris is much greater in certain orbits than others. Micrometeoroid orbital debris entails, as the name suggests, micrometeoroids and orbital debris. Micrometeoroids are the remnants from comets, asteroids, meteor showers, and the like. And ever since Sputnik, man has been creating orbital debris. Orbital debris is comprised of non-functioning satellites, rocket bodies, broken parts of satellites from collisions, explosive bolts used to store and release satellites from launch vehicles and other satellite components, and specks of paint. The smaller the orbital debris, the harder it is to track. It is believed there is well over 100,000 pieces of orbital debris less than 4 centimeters in size. While the physical composition of micrometeoroids and orbital debris may be different, and the likelihood of receiving a strike from micrometeoroids is much less than orbital debris, we group these two areas into the same environment because of their relative velocities. Recall from the Kepler's laws and conservation of energy educational aids that kinetic energy is energy in motion. Both micrometeoroids and orbital debris pack a lot of kinetic energy. On average, micrometeoroids have a velocity of 17 kilometers per second and tend to have an impact velocity to on-orbit satellites of 19 kilometers per second. Micrometeoroids can strike the spacecraft from any angle and cause great damage to the impact area. Orbital debris has an average velocity of 8 kilometers per second and an average impact velocity of 10 kilometers per second. Orbital debris tends to impact the spacecraft on the ram side, or the front of the satellite in the direction of satellite motion. I mentioned earlier that there is believed to be over 100,000 pieces of debris on orbit that is less than 4 centimeters. And objects that small tend not to have a lot of mass, such as the speck of paint mentioned earlier. So what is the issue? Recall that kinetic energy is equal to 1/2 times the mass of orbital debris, usually really small, times the velocity of orbital debris squared, very large. So the issue is velocity. To put this in perspective, a piece of debris about 3 millimeters in size, traveling at 10 kilometers per second, has the same kinetic energy of a bowling ball traveling at 100 kilometers per hour, or about 60 miles per hour. And a piece of debris 1 centimeter in size will have the equivalent kinetic energy of 180 kilogram, or 400 pounds safe, moving at 100 kilometers per hour, or 60 miles per hour. So as you can imagine, the effect on the spacecraft can be quite catastrophic, depending on where on the spacecraft the micrometeoroid or orbital debris strikes. And the last area we will cover is scintillation. Scintillation is characterized by the rapid and random variations of radio signals due to changes in the ionosphere's electron content. Scintillation actually means a flash or sparkle of light. We can see this sparkle when we look up into the night sky. When we do, we see the stars seem to twinkle. The stars are not dimming and brightening, but rather the starlight is being refracted or bent as it passes through the ionosphere due to random and rapid variations in the density of the ionosphere. Recall from the electromagnetic spectrum basics educational aid that visible light is just one part of the electromagnetic spectrum. So if the ionosphere has this effect on visible light, does it affect other portions of the spectrum? The answer is yes. Scintillation affects the lower frequency, higher wavelength portions of the EM spectrum. When it comes to spacecraft, scintillation affects the radio bands the greatest by imparting low frequency noise to these signals. The amount or the degree scintillation affects communication is a factor of satellite inclination, local time, season, geomagnetic activity, and solar cycle. The two areas that have a greater probability to be affected by scintillation are lower orbits with high inclinations, specifically around the auroral regions, and when orbits pass near the equator. The auroral areas tend to be affected by scintillation because charged particles traveling along the magnetosphere pass through the ionosphere, creating the auroras. Additionally, the charged particles form unstable areas of compression and troughs in the ionosphere. These areas of compression and troughs distort radio frequencies. Just as the auroras are stronger during the night, so are the effects of scintillation. Typically, these effects of scintillation are greatest during local times of sunset to 3 a.m. and during times of greater geomagnetic activity. Also, at the equatorial regions, scintillation primarily occurs only during nighttime. After sunset, bubbles of ionization occurs at the bottom of the ionosphere and travel upward through the night, typically ending by midnight. Lower frequency communication through these bubbles can be affected. Well, that is it on the space environment. I am Jeremy Brown with the National Security Space Institute, and I hope you enjoyed this educational aid.
Right, to close, we'll then show the Goddard Solar Dynamics Observatory, which you can see pictured at the top right of the screen there. It's quite sizable. It's over 6 metres long and 4.5 metres wide, so very substantial. Multiple cameras there detecting or pointing at the sun and recording different wavelength bands of light. It orbits about 3 Earth diameters above the Pacific Ocean, and its footprint on the ground, shown in the bottom right there, is a very strange sort of analemic sort of shape. The reason for that is that its orbit, of course, has to avoid the Earth and keep pointing at the sun at all times, so that it doesn't experience day and night, which it's able to do from that far away. So there's no nighttime interruption to the observations. Now, the recent aurora that was actually seen was the bright flare that the observatory caught at about the 6 o'clock position, shown on the left hand side there. So you can see that bright outburst that was obviously, the angle of it was such that it shot outwards and was directed at Earth, was going to intercept it about a day or so later. Now, in this particular video to close with, it's quite a large time lapse, and it's 1 frame every 8 hours for that 5 years. But enjoy, and we'll see you at the January meeting of the Mornington Peninsula Astronomical Society, as there's no monthly meeting in December usually. So I've been Peter Skilton, and hope you've enjoyed the year as best we can at this time of not being able to meet very frequently or very often due to the pandemic, and hopefully 2022 brings a lot better skies and a lot better meeting conditions.